So before we do lists, we're going to do pointers. And then Friday we'll finish the discussion on lists, and I'll actually put out your first assignment. And it'll be an assignment for doing linked lists. Okay, so what the heck is a pointer? Well, a pointer really just points to a location or number. It says, hey, this is where it's at. So in computer science, pointers are just variables that store memory addresses instead of data. And so usually you give them the address of other variables. So how do we put that into English so that we actually understand what the heck we're talking about? So if you think about a bank, they have all these safety deposit boxes, right? And you've got a number on the box, and you have a key that goes to that box. So that's how you know which one is yours. Well, if you think about the fact that every safety deposit box has a number, so you have a quick reference, you can find it. Imagine if you had to like manually count, which one was 1, 2, 3, 4, 5, 6, or as it's starting at the top left, they start counting from the bottom. I mean, how do you know? So that's why they put numbers on it. And so those numbers are literally like the address of a variable. It just says, this is where I live. This is me. Or maybe think about your street address, like the actual numbers. So this is my home right here, okay? That's an address. So a pointer in this whole little analogy of safety deposit boxes is anything that stores the number of another safety deposit box. So here's our ideal scenario. You have this really rich relative and lots of tons of money. You're like, woo-hoo, right? When you open the safety deposit box, and all there is a card in there that says what safety deposit box the cash is actually stored in. Okay, so you have that one safety deposit box, but all it stores is an address of where the money is. So ideally, I left you the money and the key and the card, and so you can go get the actual cash. So that card that is storing the location of the other box. So that's the equivalent to a pointer. You're just saying, hey, no, the money's not in here, it's actually over there. And it tells you where it's at. So that's what pointers do for you. So when you declare a pointer, so there's the notation. There's the asterisk notation and the ampersand notation. So hopefully I can, and we actually, in computer science world, we call that asterisk a splat. So you look at it, it looks like a splat, right? Looks like a bug got splatted. We just call it that. So when you declare an actual pointer, you use the splat in front of the name of your pointer to indicate that that is a pointer versus a regular variable. So the first one is just a pointer. The second one here, the int, I have my splat pointer, comma, a non-pointer. Okay? So what that is doing, the first one is actually a pointer of type integer. The second one is just a variable of type integer. And then the third one here is just two pointers being declared. You notice they both have that splat in the name. So on WebPortion, I uploaded this pointer file here, and it has different words in it, so maybe it'll make more sense to you. So on line 5 is int x. You're just creating a variable called x, and its data type is an integer. Everyone good with that? Okay. On the next line, we are declaring a pointer of type integer. And you know it's a pointer because it has the splat in front of it, right? So when you're doing the declaration, you always do the splat. So, and then the text that goes with it is there's a pointer to an integer, and the splat p is an integer, so the p itself is a pointer to an integer. So the data, you can't have a pointer of a different data type than what the data itself is. So then what we're doing on line 10, is that line 10? That's a simple well here. How about line 9? On line 9, we are assigning the address of x to p. So we have this pointer that we created, but it's not equal to anything yet, right? We just created it. That's all we did. It has no value when you do that declaration at line 5. It has no value, it just exists. That's it. On line 9, we're actually assigning some value to it. So when you use the ampersand, what you're saying is address of. So I like to use alliteration to help me remember stuff. So you think the ampersand A is the address of A. So if you think about it from that perspective, that's how it's easy to remember when you use the asterisk and when you use the ampersand. So the ampersand is when you're assigning it to something. So I'm trying to give my pointer P the address of my X. So you'll see when we output this, the console will be just sitting there waiting for us to enter some value. And so what's going to happen is it's going to get the address of that data that we're putting in there. And then what happens is our P is going to actually be represented that same data. So you see I'm going to scan in my X, okay? Up here I said my pointer P is equal to the address of X. That's because a pointer is an address, right? So we have to put the address of that X to set it equal. So when I'm doing the scanf, I'm going to store in the address of X, the value I enter on the keyboard, and then I'm going to turn around and print it out. Because now this next line here on line 11, this is what's called dereferencing your pointer. Because you say, hey, I want the actual data that's there. I don't want the address, I want the data, right? And so that's called dereferencing. So you'll see this run. Okay, so it's not cramping here or anything, but it's just saying, hey, give me some value. So I'm going to put in the number 6, hit enter, and it returns back my 6. Okay, so what happened was we're going to scanf. So remember, that's how you get input from a user, is scanf, right? And so I put in my number 6. So it's stored at that address of X, the number 6. And because I set my pointer equal to the address of X up on line 9, that when I print that out and I print out the splat P, I'm getting the data value, not the pointer itself, the actual data value that's stored there. So that is what's called dereferencing your pointer. So here, the pointer. There are 2 ways to use your pointer. So you have it give the actual address to another variable. So that's using the pointer without the asterisk, right? So that's this right here. I'm using my pointer without the asterisk because I want to assign to it the actual address of another variable. I am assigning to this the address of, and you know it's address of because I put the ampersand in front of it. So think about ampersand means address of. Okay, so use that alliteration to help you. And so because I'm assigning it, and P is a pointer, it stores an address, I don't need that asterisk. I'm just going to use it as a pointer because I'm doing address and address. Does that make sense? Did I lose anybody? It's okay if I did. So it takes a while. It's kind of coming. Is it coming back a little bit? Okay. So P is a pointer. A pointer is an address. So I want to assign the address of X to my P. So I have that actual physical location on the computer in memory where that guy lives. So that's what we're talking about right here. Give it the actual address to another variable. X is my variable. Simply use the name of the pointer without the splat. Okay, so that's what I did in the code. I have the pointer, P, without the splat, and I'm setting it equal to the address of, using the ampersand, of my X. Are we good with that? Okay. Now, if you want to access the actual memory location to get that data, you want to go, you're going to open that first safety deposit box, and it has the key and the card that says where the cache is. So you're going to actually go get that cache. So that's what we're doing now. We want the actual data that's stored at X. What is the data? So, but we have this pointer to it. So how do we use that pointer to get that data back? And that's what we do. We call dereferencing the pointer. So you have to use the asterisk or the splat again to actually get the data versus referencing the pointer itself. So that is called dereferencing the pointer. When you put the splat in front of it, you're saying, give me the data. So what you do is you're going to follow that memory address and go to that address and go, what information do you have for me? So that example is indicative in this code right here. When I say print out asterisk P or splat P, saying give me the data that is stored in your location. Make sense? Yeah? No? Any no's? Okay. So here, pointer declaration. So I have my splat points to an integer is a pointer because when I'm declaring it with the splat, you're saying I'm a pointer. I'm going to store a memory address. Here, one pointer and one regular int. So the first one is a pointer, and you know that because there's a leading splat on it. And the other one is just a regular integer because there is no splat on it. It's just the name of the variable. And then here is an example of just two pointers on a single declaration line. So this is the code that's actually in the assignment itself, line itself, the pointers.c that's uploaded to web courses. So let's look at this really close. So we have our standard I/O header file in order to do input/output, and then we have our if main because you always have to have a main. And then so here I'm just declaring a regular integer and I'm calling it x. Okay. Now the next one I'm declaring a pointer called p, and its data type is an integer. And we know that it is a pointer because it has the splat in front of it. So now I want my p, my pointer, to have the address of my integer x. So in order to do that, on the left-hand side, I use my p without the splat because I'm going to set that address of my p. And I'm going to set it equal to the address of my variable x. So in order to get the address of a variable, you use the ampersand. So again, that alliteration, just keep playing that in your mind and it'll stick and you'll actually get it. So then I do a scanf. So I want to put in some numbers, so I'm prompting the user for data. And I want it to be of type D for decimal data, decimal meaning integers, not floating point. In computer science, decimal actually is base 10. It's your it's a numbering system. So we don't use the word decimal in computer science unless we're talking about the actual data type. So here I'm going to receive an integer, so we use the D, meaning a decimal value, and then the address of x. I want to store whatever the user enters on the keyboard. I want to store that in the address of x. Make sense? Yes?
You forgot the ampersand in front of the x. Would it still store it as just a regular info, whatever you have in there? Or would it still be the address that you declared as a pointer?
Well, let's do that. Okay, so it wants some number. Notice nothing came back. Okay. Well, and it crashes. That's awesome. See? Okay, so what happened was, because I'm trying to output the data stored at P, I said P is equal to the address of X. I stored this data in X itself, not the address of X. And so this no longer works. It's completely broken. Because you said that P is a pointer, so it stores an address. And then you said P was equal to the address of my integer X. But I didn't put anything in the address of my integer X. So it breaks it.
But what if you said that P was, instead of saying equal to the address of, what if you just said P is equal to X, but still had it declared originally at the top there?
Okay. All right, expecting some data. Crash and burn. Okay, because pointers store addresses, they don't store data. All right, so we're using this completely wrong, and it's going, I don't know what you're doing, I can't function, I'm just gonna crash. Okay? Any other what if scenarios? So here I'm getting data from my user. I'm saying store it in this address of X because that's where I want my data to live. I want it to live in the address of X. And then here I'm going to dereference my pointer because I want the actual data value. And so I can actually output that data value. And then the get care is just to do your return so you can exit the program. So are we comfortable? Yes.
Now, if you, on the program side, assign a value to X without the ampersand X, not an input, but an actual in program,
Okay.
that would be the value stored in that address, right?
Absolutely. So what he's asking if we initialize our X. So let's give our X some value. And skip the scanf. We're just going to go ahead and output our P. So here, now X actually has a value. So X itself still is something at this memory location. And we're setting P equal to the address of X. So when we dereference our P, it says give me the data stored at P. You see that it comes back 23.
So why is it that when you're picking a variable, and you're basically trying to assign it to X instead of value, why do you need to use ampersand sign? Why would it be assigned that value to X?
Because when you store data using input-output, when you're using pointers, you have to do the address of. Because it says, okay, yes, I know I have this variable int, X, but X right now has no data. Okay, it lives somewhere, you have a memory location for it when you declare it, but it has no value. So at the address of X, put this value in there. So when you do the declaration up here and you initialize your data, so you're saying in X now has a memory location, okay? You're setting it equal to 23. So you're saying at my memory location for X, put this value in there. Now, when you're dealing with input-output, in order to put a data variable in that address location, you have to use the ampersand. It says, okay, at the address of X, put this value. Yes, sir.
So can I go back to your lockbox now?
Okay.
So what you're saying is that for X, it's in a lockbox.
Yes.
X has something inside.
X is a lockbox.
Yes.
Okay. It has a location. It exists at lockbox 5.
And P is another lockbox. But inside of it, it tells you if it's pointing to X, it tells you what's inside because it contains
Yeah.
So you're talking about pointers, it's kind of like a lockbox telling you what's inside another lock.
Yes, exactly. And those are the words in your understanding versus mine. Here. So the first lockbox, okay, X, it just all it has is the location of where the real money's at. Okay? Anyone else? in order to do linked lists, you have to be comfortable with pointers. So up on web courses is an example of a linked list code. So the linked list code, when you do this, you have your data portion of it. So my data portion is typed int, and I'm just going to call it data. And then I create a pointer to it, which is my other attribute of my struct, and it's of type node. So it's of its own type here. So I'm going to say I have this struct type node, and I'm going to give it the name next. And because it's a pointer, we're going to do address up. Slack, excuse me, do the slack, because it's going to be a pointer, right? And then we have a overall instantiation, excuse me. So here, the Slack head is just giving another reference to this node.
Yeah, basically instead of trying to.
Okay. So what the heck is a linked list, right? It's just an abstraction of a list. So it's just a sequence of nodes where each node has a reference to the one following it. And so that's why we use that next. You apply it most often, we either have a next or the previous, so that we know which way we're going. And so if you think about that concept of an array, right? So that instead of just having an array of the data, we actually have this contiguous memory, okay? So each node is stored in a continuous memory. However, with arrays, they're a fixed size. So sometimes you don't know how big your data collection is going to be. So that's why we like linked lists, because it allows us to insert and delete elements, because in an array format, you don't have that option. When you're doing an array, it means that you have, let's say you have an array size of 100. If you insert an element after the 10th element, everything is pushed, right? Because you're inserting something in the area that's already there. So how do we work around that? We work around that using linked lists. We use linked lists because they're dynamic. So who's taken object-oriented yet? Some of you? Okay, so you did array lists. Did you do array lists and object-oriented?
I think so.
No. Some of you did, some of you didn't. Okay. So in object-oriented programming, in Java itself, we use the same ability to have a collection of data when we don't know how much data we have. And we call that an array list. So instead of using an array, because arrays are fixed size, you have to know how big your data is going to be when you use arrays. Well, we don't always know. And so that's why we use linked lists. So in C, they're linked lists. In Java, you would use an array list. They do the same thing for you. They give you that dynamic ability to increase or decrease your data set as needed. So you don't have to know up front how many you have. So here, each node doesn't necessarily even follow the previous one in memory. So when you do an array list, it takes a big, huge chunk of memory all at once. So we get an integer array of 100 elements. It's going to do contiguous 100, so it's going to take up like 400 bytes. And it's all in this one little chunk. Well, the great thing about linked lists is it doesn't have to be sequential as far as memory is concerned, because it can put it anywhere. It's awesome. And so the pointer that's part of that struct is what allows you to just save your data wherever, instead of having to do that contiguous memory block. And so here, when we do the insertion and the deletion, you only have to change a few nodes at a time. So you're not pushing everything. You're not upsetting the sequence of the data like you would in an array. And so you know, what are some potential drawbacks to a linked list? And sometimes it can be a little bit code intensive to get the So you have to do a little bit of work to get around that. So a linked list is just an ordered collection of data. You have this big pool of data and you need to store it. And so we don't really want to use arrays because we don't always know how big our data set's going to be. So we're going to use a linked list. And so for each of those elements or nodes, we use the term nodes for each element. Elements are more indicative of arrays. We use the term elements in arrays, but in linked lists, we call them nodes. And so they contain the location of the next element in the list, and it doesn't have to be contiguous memory. It can be anywhere. And so each node really has two parts to it. It has the data part. So let's say that my example, code example, only has just one variable of data, but you can have multiple variables of data where I could say, we could change this. So it's your UCFID. That is that programming. So that would be the number. We can say, what is your GPA? What is your age? You know, just, there's different data. So it's not always just one piece of data. It could be multiple pieces of data. It's just dependent upon what you're trying to simulate in that case, or you're trying to replicate. But you always have that pointer in there. So the very last part of this is that struct node. You're creating an instance of the node itself, and you're giving it a pointer so that you can put that next. So this next right here is what we're talking about when we're talking about next here. The link part. This link is used to chain the nodes together because again, it's not necessarily contiguous memory, but you need to know where it's at, right? You know, kind of like pin the tail on the donkey, or like, yeah, I have no clue where I'm at. So you're giving it and telling it this is where the next guy is at. And so it just contains that pointer variable that points to the next node in your list. Very, very, very frequently, we just use the word next because it makes sense, so that when you look at it, there's this logical correlation to what in the heck that you did in the first place. And then sometimes when you're traversing a linked list backwards and forwards, we'll also have another pointer called previous, very commonly implemented. So what we'll do on Friday is go into more detail about this. So many times though, you'll see this when you have to do a traverse of a linked list. You'll see it has two pointers instead of one, where it has the next and the previous, so that you know exactly where you are at all times in a linked list. Does that make sense? Maybe? Okay. If it doesn't, you can tell me no. I'm totally cool with that. So this is just an example, a very dumbed down example. It's very simple. You have data, and then you have your pointer to the next node in our linked list. Yes, sir?
Is the next node in the linked list going to have like an address of next or something? Like how is it?
Oh, absolutely. Yeah, so you just have a whole bunch of these nodes, okay? And they're all linked together. And you know that they all go together because they say, okay, so you have the first guy, and you say, hey, I'm the first guy in the list. You're going to be the second guy in the list. And I know where you are because you gave me your address. And so I know how to find you. Sounds kind of stalkerish, doesn't it? But anyway, and then you're the next guy in the list, and you know where he is because he gave you his address. So you're not contiguous. You're not all in a row like an array. You're kind of all over the place, but they know how to get there because you're saying, I know your address, so you're the next guy. And you say, well, you're next because I know your address. But then what if you want to go backwards? What if he wants to know, well, who's the first guy in my list? Well, that's what the previous is for, so you can go backwards, okay? So the next says, who's next? The previous says, wait, who's before me? So now we have a previous. He goes, oh, I need to go back. Wait a second. And he goes, oh, previous, I know where you are because I have your address. So you're kind of like swapping, it's like swapping phone numbers to text each other or something, right? You know each other if you have each other's phone number. So you have that reference back and forth. So that's what the previous and the next pointers do for you. They give you the address of that memory where the data is stored, so we don't have to use an array, because arrays are limited. We don't always know, okay? So when I agreed to teach this class, there's 250 people. And I'm like, that's fun. And then all of a sudden there's 700. I'm like, whoa. So initially, I thought I only needed memory for 250 students. Turns out I was completely wrong, and now I need memory for 700. Well, in an array, I'm completely posed, so I only have room for 250. Well, the university said, oh, no, you're going to use a linked list, because we're going to give you as many as we can, so we're going to give you 700 instead. Or more, or less, we'll see what happens. So that flexibility is why we use linked lists instead of arrays. Yes?
I've never seen a format with a dot part. What does that mean?
Which one?
The very end of dot head.
Oh, the flat head. So what that is you are creating an instance of this struct node, and you're naming it head. Okay? So it would be the same, see right here? Struct node, splat temp, splat right. That's the exact same thing here, but you're doing it while you actually create the structure. Does that make sense? So you already have one instance of this node, and it's called head. There's a pointer to it called head. Good? No. Okay.
Like in the array, you can reference it.
Oh, you can. Yes, but there's more work to it. And as we get more in depth, I'm just trying to make sure we all get to the first part of the pointer before we start talking about actual conversing back and forth. Yes, sir. Yes. Okay. So let's look at our main. Let's see how many slides I got left here. Okay, let me talk about this, and then we'll go over the code. So if you think about each node as a record, anyone take the database classes yet? Anyone do databasing yet? All right, probably if you've done databasing. Okay, so when you store data in a database, it's called a record. It's like all this information. So it's like there's this big, huge database that has all of our information in there. There's student information, there's staff information, but all of us pretty much have the same information that's stored in this database. You have a UCF ID or a PID, depending on what the heck your record's in. Then we have our NID, and then they have our names, they have our addresses. They definitely have a social security number. They want to be able to find us financially if we decide not to pay our student loans back. And there's information about your major. There's information about classes that you've already taken. There's information about your GPA. So that's a record in a database. It's all this information about you on a single line. Think of it like Microsoft Excel. You know, each row is considered a record. If it has multiple pieces of data, you're talking about one thing. Okay? So that's a record. It just has information that's all about something. So the first part of our record is all about data, okay? And then the second part of our record is says, hey, where is the next move in my list? So that's always part of your record, so that you know where the next guy is at. Then you also have to know where the head of the list is, because you got to know where to start. Now, if we're doing an array, what position is the head? 0. You're like, ooh, that's easy. Linked lists don't have that concept. So we have to store that. We have to have something that says where is the beginning of my actual array, my linked list, excuse me. So that's why right here we have a head. As soon as you create that struct and you want to know where is the beginning of my struct, of my linked list, it's right here because it's in the initialization. And we use that keyword head to indicate that that is the very first node in our linked list. Does that make sense? So node of our list is dynamically created as we need it, just like array lists in Java. So it gives us that flexibility where we don't have to know how big it's going to be, how much data we have, It's like my analogy. I signed up for this class because I gapped out of that class with 250 students, and they went, just kidding, there's 700. Have a good time. But it's fun, not a good time, it's fun. So from our very first node, we can find out who the second one is, who the third one is, who the fourth one is. But if we know that we're definitely going to be traversing data back and forth, and this leads into what we'll do on Friday, talking more about this list, we also need that previous. We kind of want to be able to get back where we came from too. Kind of like Hansel and Gretel with the breadcrumbs to find their way back. So how do you get back to that first node? And so you have that is the very beginning of your node list, so you can keep track of that. Like, hey, I'm number one, I'm the dude, I'm in charge. It's like what's that silly little dance, the Congo line or whatever? There's the first person, and kind of everybody tags on. All right, so there's always that first person. That first person falls down and you're all toast, right? Usually you're toasted if you do a Congo line in the first place, and hey. All right, so you can call it whatever you want, but usually we use head. Okay, so here, the great thing about you guys being in a 9:30 class, if you don't get it and you have time, you can come to the 11:30 class and hear it again. Isn't that awesome? Think how much quality time we can spend together this semester. Okay, so hey. I'm just kidding. Okay, so here's my struct, here's my node. All right, so let's just make it easy, and let's just roll this back down to a simple implementation before we get all crazy with difficult ones. Change this guy back to data. Okay. So in this file we have different functions. I'm going to tell you, I'm going to put out your labs on Friday, and it's going to be a lab to do linked list. So if you download this code, it's really going to help you do your lab. Just saying. Now, if you want to suffer on your own, more power to you, but I do try to help you be successful. All right, so we have this function called add. This means we're going to add something to it. I'm going to
Declare, Jeff Pointer's asterisk head. Declare that it's a structure and tell about it. Is that what happens?
yes, because they're not initialized yet. So everything is not. It was like when we were doing the little simple pointers guy, and when I use X instead of ampersand X, it didn't let me run. I had no idea who I'm going to run. Okay, but when I initialize the X to 23, it was like, hey, I'm bored. Okay, because it was actually initialized. But before that, when the X is not initialized with anything, and it didn't store anything in the actual address, I just did a scan out on the X and went, nope, I got nothing. 20 was no. And that's what you saw nothing. And then it actually worked.
So after you create the star tag, it actually creates the structure for the main function.
Yes. So you actually have in the main. So you could actually declare it in the main, but this way you know that you have that very initial one, because as soon as that application uses that, it already uses it. So here we have some functions. We have an add, we have an add after, we have an insert, and we have a delete, and a display. Oh, we're gonna count. Okay, here's our main. All right, so this is the part where that matters. All right, so here's our main. We're declaring an integer called I, and we're declaring an integer called num. And then we're just going to create a pointer of n that points to our struct type node. And then we're going to initialize our heads to null. Because one of the things about pointers, and this is in Friday's lecture, but not initializing your data can be really, really dangerous. By default, it's null, but you definitely want to know that it's null. So I'm really a really big fan of initializing my data. I definitely set it to null right off the bat, so I know that there's no way that this pointer head can accidentally have some memory address in it that I didn't know. Okay, so it wipes it out. It says, hey, I'm not. Because when we created that struct and we put an asterisk head at the end of it, very first node, and then we're gonna head to that very first node. So you just, it makes sure that you don't have any funky data. Yes, sir.
Are you also able to flip to zero with the same thing? Because in some languages, for example, they don't really understand null all the time, but zero is the same thing.
Pointers are, I'm using this term very loosely. They're like an object. They have multiple pieces to it. So initializing a pointer to 0 is not valid. I mean, we can try it, but null is, because you're talking about memory addresses, you're not talking about an actual integer itself. Let's see if this will even compile. Nope, it says, oh, hell no. Okay, so it doesn't even understand it.
Well, you also, because you defined the struct accidentally, you left asterisk rev instead of asterisk next, that compilation error may be good.
Oh,
Now it doesn't know what next.
you're right, you're right. Thank you, thank you, thank you. Okay, so it does work. Okay. In theory, it works, but null is better. Because 0 could be a valid address.
So it's just like in C++, for example, the compiler, and then what you're using, it's always understand null, but it will understand zero. So that's why I was curious.
But 0 is potentially an address on your computer. You could have a physical address of 0. So that's kind of risky. You know what I'm saying? So null is better. Null means nothing. Nothing at all. Does that make sense? Why you would use null instead of 0? Yeah. I mean, so yeah, 0 works, but 0 can be a valid memory address. So you just kind of want to be careful with that. Okay. What time is it really? This says 10:23. This says 10:17. All right, so I have 3 minutes. All right, we'll go over this again on Friday. But so this is just the beginning of what we're talking about regarding a linked list. So here, what this main is doing for us is actually letting us create a linked list. So it's asking you to, what do you want to do? It's giving you a menuing option here. And if you say insert, so if it's going to do a check and say, hey, this is just validating the data, the user input it. So if they input some value less than or equal to 0, then you didn't put in a real number. But if you did, it's going to take the value of I, because it's storing whatever number you insert to the address of I, and it's going to look at the data of I, and it's going to find out which one of the menu options you're picking, right? So we have 5 of them, and then here we have a default because you could potentially input any number, 0 through whatever. So if it's not 1, 2, 3, 4, or 5, it's going to go, hey, that's not a valid option. This is just giving the user feedback of what they're doing. And so when this happens, depending upon which one we're doing, so the first one is we're going to insert a number, right? And then, so we're going to get that data from the user, and we're going to store it at this address of num that we declared up here, declare it an integer of type num. So we're going to store the data at the address of num, and then we're going to pass that data to this function insert. So then we go up here, we look at our function insert, and we're receiving an int, and our return type is void. So we're just going to insert this into our linked list, and we'll talk about the rest of this on Friday. Okay, so take a look at this code, review the pointers as well. Try to get familiar, get comfortable with pointers. Yeah, and then on Friday we'll